Welcome back. We're going to talk about the electric field equation. So I'm going to go ahead and write it here for you. E is equal to K, which is a constant I'll talk about next. Electric field. Q over R squared. Q is the source charge, the source of that electric field, and R is just some distance in space away. So I'm just going to kind of move this off to the side, shrink it down so that we can work with it later. Let's see. There we go. Much smaller. Good. Like I said, I told you I'd define K for you. K is, I'm going to use some engineering notation here. It's made up of, you guessed it, other constants, but all you really need to know right now is the value for it, and units on it are meters squared per coulomb squared times Newton there. That's important later if you want to do any dimensional analysis. And it's kind of in our way as well, so I'm going to shrink it way down and move it off to the side as well. And then we'll keep going. So I'm going to have a charge here, and we're going to say that that charge has... let's not do that. Let's say we have that charge right there, and we'll move it over just a little bit. But we'll say that the charge has a value, come on, equal sign, of 4 nanocoulombs, which is just 4 times 10 to the negative 9th, again the engineering notation, coulombs. And I don't want that in the way, so I'm going to bring it over here, way down. Okay, so moving right along then, I'm interested to know what the electric field is at this point over here. What is E? I wonder. Well, how far away is it? We need to know that. That's the R squared part. Well, I'm going to say it's 3 centimeters, which of course is just 3 times 10 to the negative 2 meters. Good, good. So, we have all that. I'm going to switch the colors up again, and we're going to look at the equation. We're just going to do some plug and chug, because right now we just have one particle, and we're interested at this one point, however far away. And we want to look at it and say, what's the field there? So, E 99, not 99, but 9E9. And then we square R. So real quick, doing some dimensional analysis here, you're going to see that this meters squared term going to cancel out with that meter square term, and we're going to drop a coulomb. So we can expect that whatever our value for E is, the units are going to be newtons per coulomb. Okay, so we can kind of anticipate that, newtons per coulomb. For the actual value, we're going to use a calculator. And I didn't even mean to do this, but it turns out that it's 40,000 newtons per coulomb. That works out really nicely. You could, of course, say that it's 40 kilonewtons per coulomb if you really want to. And we'll just stick with 40,000 newtons per coulomb. That would be our answer. So that's cool, right? But I imagine you probably want to see more, because we're not just going to sit here and find what's the field, some distance away over and over again. And in fact, we're going to be adding particles, and they'll be in all sorts of arrangements. They'll be in lines. For example, let's see. Let's try this. They'll be in lines. They'll be in triangles. They'll be in squares. Well, quadrilaterals for that part. And any other shape that, geometric shape that I care to think up. But for now, I think we're just going to stick with some in line for you to try out. So I'm going to clear all this mess off. If you need to go back and look at it, you can do that. But I'm going to go ahead and pause things right now so that I can set up a problem that I want you guys to look at before you come to class. Okay, so I'm going to leave that equation up there to start with. And actually I'm going to show you one more example of kind of combining electric fields here. I'm going to have a charge there that I'm just going to call sodium ion. And then I'm going to put a charge over here that I'm going to call a chlorine ion. And if you know a little bit about chemistry, you know that the two of these can combine in a crystalline formula to form table salt. What we're going to do is we're going to look at the field strength between these two. Now, it doesn't look like I gave you anything to work with as far as a charge is concerned, but this plus is going to be actually, hold on, let me get rid of some stuff. Okay, that other charge value is gone now so that we can continue working with these charges. You'll see the plus and the minus on the sodium and the chlorine. That just speaks to the fundamental basic charge Q, which is 1.6 times 10 to the negative 19th coulomb. So that's just a really small amount, and that's just the charge on an electron, also on a proton. But for our purposes here, we're just going to use that as the fundamental charge for the sodium and the chlorine. So each of them have the same charge, just one has an extra electron and the other has a deficit of the electron. That's how it forms that bond. So distance that I'm going to separate these by, so the distance these are going to be separated by, we'll call that x. Well, x is going to be 2.82 times 10 to the negative 10th meters. So it's a really small distance. And we're going to shrink that down, set it over there so that we can work with it later. Just like that. So we can reference it as we move forward. So I'm going to go ahead and finish out the setting up what I want to know. Now in this particular instance, I'm interested to know what the electric field is at a point between the two, so right here. So that's going to be half the distance x. So I want to know what the electric field is. Well, the electric field follows something fancy sounding that's called the principle of superposition. I know it sounds like really awesome, and I guess it kind of is, but really all it means is you just add everything up like a vector, and when things are in a line like this, it's really easy to do. You just kind of add everything up. So the field at this point that we have right here is going to be the field from the positive charge, and added to it the field from the negative charge. And remember, when we're drawing these fields out, it's always a good idea to kind of draw direction. Okay, so from our standpoint, we always treat the test charge as a positive charge. A positive charge here would experience a push that way, right? So that positive charge would experience a push that way. But it would also experience a pull that way from the chlorine, right? Because the negative side is going to attract that particle. So overall, we know that our field is going to go to the right. So it's going to look something like this. I'm going to pick to the right to be positive. Okay, and so when we calculate this, it's going to look like this. You know, our net electric field, because it is a vector, our net electric field is going to be E from the sodium plus E from the chlorine. And because the only real difference is one's an electron, or one has an extra electron, excuse me, and the other has a deficit of an electron, their charge is going to be the same. It's just in magnitude. It's going to be the same in magnitude. So both of them are going to be possessing a Q of 1.6 times 10 to the negative 19th. So when we write this out, we'll have KQ for the sodium. Here, let me back that up just a little. We'll have KQ for the sodium over R squared, and we'll talk about what R is here in a moment. And then we're going to add to that KQ over r squared for the chlorine. And there's a trick here. There's an r squared there, you just have to believe me. There's a trick here because the distance to the center is the same either way you come, right? So our distance r that we're going to use, which is going to be half of x, so I'll just go ahead and make a note there that r is x over 2. So that distance is going to be the same, and I've told you that the magnitude of q is going to be the same, and you don't need to consider q as positive and negative because we've already taken care of that with the direction of our field going to the right. So you don't have to put in a plus q or a minus q here because we've already taken care of direction, right? So what you're actually going to do is just add these two. So kq over r squared plus kq over r squared is 2kq over r squared. So what this will look like for r net, just the magnitude here, so I'm not going to draw the vector hat, is 2 kq over r squared, and remember r is x over 2 squared. And then we can start plugging some things in here. So that's going to look like, with this 2 and this 2 squared there in the denominator, what we're actually going to get, that 2 squared in the denominator is 4, which flips up to the top. We're actually going to get something that looks like 8 times, and then we'll go ahead and plug in 9e9 times q squeeze it in there, and then all that's going to be divided by the 2.82 e to the negative 10th meters, and then we square that. So I'm going to fall back here and use my calculator, and then I'll write the solution up here saying what E net is, and then I'll give you one to play with that we can start our discussion in class with. So hold on one moment. I'm going to pause things while I calculate. Okay, so what this is going to end up looking like then for E net is 1 point, I'm going to carry out lots of decimal places here, 4486 times 10 to the 11th, oh, hold on, 10 to the 11th newtons per coulomb. So I know that's kind of shoved in there, but that's the electric field there between those two particles. So let me see if I can grab that out of there. Nope, the whole thing wants to move, so we'll just leave it alone. But what I'm going to do is I'm going to go ahead and clear some of this stuff off so that I can present another problem that I want you guys to look at. Good, we're back to this setup. X is still the same, but what I want you to look at, the point of interest that I want you to look at, is going to be at a spot a little bit closer to the chlorine. Okay. So at this spot, what I want you to look at it as, this distance is 3/4 of x, and this distance is 1/4 of x. So now this is going to be R for Na, and this will be R for the chlorine. Everything else should be about the same for you. Don't want to spoil it too much, but I want you to go ahead and give that a shot so we can talk about it at the beginning of class next time. Well, until then, hope you have a good day.